Now that we have gone through CLRM assumptions and the numerical properties of OLS estimators, it's time to look into statistical properties of OLS estimation. So as I said before, statistical properties, they are satisfied only and only if the assumptions from CL1 to CL5 are satisfied. So these are considered as the properties that hold under these assumptions about the way the data is generated. So only true. This is only true if the assumptions are met. Okay, this is very important, so keep that in mind. So given the assumptions of classical linear regression model, we say that the OLS estimators beta naught and beta 1 cap, they have some desirable properties. Okay, and these desirable properties are what we refer to as the statistical properties. Another name for desirable properties is statistical properties. Okay, so now we'll look into what these desirable properties are. So basically, these statistical or desirable properties is what's explained under Gauss-Markov theorem. So what does the Gauss-Markov theorem actually say? It says that if assumptions CL1 to CL5 are satisfied, the OLS estimators, that is beta naught and beta 1, they are considered to be blue. So we'll go through what this blue stands for. Okay, so in blue, E refers to estimators. Estimates. We are saying that if the conditions of the assumptions of CL1 to CL5 are satisfied, the value which we get for the beta naught and beta 1, the estimators, okay, they are considered to be unbiased. And they are linear as well. So these are linear unbiased estimators. So what does this B refer to? It says it's the best linear unbiased estimators. Now if you see, actually there are different ways to find beta naught and beta 1. I've explained this before as well. See, there is OLS method, there is method of moments, MLE, there are different ways like this. But if we use the OLS method in order to find the beta naught and beta 1, then these estimators are not only unbiased, they are not only linear, but they are considered to be the best. So how do we actually determine whether an estimator is best or not? So what we refer to as best is, and the estimator which has the minimum variance is considered to be the best one. It's the highly efficient one. The most efficient one or the best one is the estimator which has the minimum variance. So since OLS estimators are not only unbiased, they are not only linear, since they are the ones which having minimum variance, they are considered to be blue. Best linear unbiased estimates. So the thing is, this minimum variance is very, very, very important, because when we are using this, especially in hypothesis testing, if you all remember, in hypothesis testing, when we calculate the value of the test statistic, remember the test statistic formula? That is T test stat is equal to beta 1 cap divided by the standard error of beta 1 cap. Okay. So when this has minimum variance, that means when the denominator is low, then T is big, right? So when T is big, it's hard or easy to reject H naught. Your guess, guys. When the variance is small, or if you all want, we can consider it the other way. That might be probably easier to catch. Now let's say the variance is very high. When the variance is very high, your test statistic is going to be low. So when your test statistic is low, it's going to be hard to reject H naught. Yes. Okay. So what does your H naught say actually? Usually we write H naught beta 1 equals to 0. Why do we write it like this? Beta naught plus beta 1 x. When we say that beta 1 is equal to 0, we are referring to as this having no effect on y. So if we can't reject H naught, that means we are saying that H1 is where beta 1 is not equal to 0. That means this having an impact on y. Okay. H naught means there is no impact. H1 means there is a significant relationship between the independent and dependent variable. This is what we want to show. But because the t stat is small, we are not able to show H1. It's hard to reject H0 means we can't reject H0 in order to prove a significant relationship. Okay. So when the variance is low only, we can show that there is a significant relationship, and that is why we stress out the importance of the variance being the minimum. Okay. Linear, you all very well know that beta naught and beta 1, it should be linear in y. What does it mean by unbiased? Unbiased means, guys, that the expectation of beta 1, it should be equal to beta 1. What does this mean? The expectation, that is the mean of the sample beta 1 which we get. Now you all might wonder, what is this? We only get one value for beta 1, then how come we get the mean of this beta 1? That is actually, now we are only taking one sample and finding the beta 1 value for one sample. But actually, if we take all possible samples of same size, okay, and if we recalculate beta 1 for each and every sample which can be taken, then we have multiple beta 1s, okay. So we take all that multiple beta 1s, add it together and divide it by the number of beta 1s, we'll get the mean of beta 1. So if the mean of the sample beta 1s, that's the estimated values, if that is equal to the population, true population value, that is beta 1 without a cap, then this is considered to be unbiased. So if CL1 to CL5 are satisfied, OLS estimators, they are unbiased regardless of the sample size, guys. I'm stressing out this point again because, okay, this is irrespective, this is held true. Okay, when you satisfy CL1 to CL5, OLS estimates will give you this, irrespective of the fact whether the sample size is large or not. So you don't have to worry whether this is a large sample or small sample. Your estimators are anyway gonna be unbiased. For small and large, this applies. But if you take other methods like method of movements of maximum likelihood estimate, when it comes to small samples, this condition might not be held true. That's why we say OLS is one of the best methods, because not only it satisfies unbiasedness regardless of the fact whether it's small or large, it is also considered to give the best estimates, is the most efficient with the mean minimum variance. Alright. Other than the Gauss-Markov theorem, other than what is explained, so now desirable properties is what's explained by the Gauss-Markov theorem, which says BLUE blue. Other than that, we have two more properties as well. That is, one, it says consistency. It talks about the estimators being consistent. So what do we mean by consistency is when the sample size increases, we say that the estimates, they converge the true population parameters. Estimates, that is beta naught and beta 1 cap, they are set to converge. That means get closer, not equal guys, very close to the population parameters. So when you increase, it will ultimately come very close to the population parameters, that is beta naught and beta 1 without a cap. So this can be written in notations in numerical terms like when the limitation of your sample size approaches infinity, it is said to be beta 1 is said to be equal to the population value. Alright. And the other one is that we say the estimators are not only consistent, they are asymptotically normal. Asymptotic normality is another property, another statistical property. This is basically like the central limit theorem, guys. In central limit theorem, what did we say? That when the sample sizes increase, regardless of the fact whether it's coming from a binomial distribution or Poisson distribution or any of the distribution, it is approximately normal. Likewise, here we say that the distribution of estimators, the distribution of the estimators beta naught and beta 1, okay, they become approximately normal when n increases. Regardless of the distribution of the error term. Alright guys, so going forward we'll be learning how beta 1, we don't consider beta naught that much, okay. Actually when we say estimators, both beta naught and beta 1 are included, but we don't talk much about beta naught, we only consider and focus on beta 1. So we'll see how beta 1 is unbiased, how it's linear, how it's considered to be best and all, right? So starting off, we'll see how it's linear. Formula of beta 1 is x minus x bar, y minus y bar. Take the summation and divide it by the variance of x, which is x minus x bar whole thing square sigma. Okay. So likewise we've learned before, I can write this x minus x bar by writing simple. Okay, I have to write the subscript now, if not you all might get confused. Y and here also we have xi. Okay, so instead of this I can write simple xi, and instead of this I can write simple yi divided by Can I simplify? Yes, instead of this one over here, here also I can in the denominator also I can write it as simple xi square now. So it will be xi square. Now because of some magic, this becomes sigma xi. This simple yi becomes capital yi. Magic, guys, magic. Tell me how I got this actually. This simple yi, what does it refer to? It means y minus y cap. Now I am writing y capital yi. How did I get this? Okay, let's see. How did I got that? So let me write this equation like this. Instead of x minus x, I am writing simple x I. Let me keep that y I minus y cap as it is. So this divided by sigma xi square. Alright. Now I'm going to cross multiply. That is, I'm going to multiply this with this and multiply this with this. So when I first multiply, it will be simple xi, capital yi sigma. Then next it will be minus sigma xi y bar. Okay, I hope you all got this part. How did I get that? This xi multiplied by this is this. Then if I multiply xi with this, then it's minus this. Okay. This can be also written as sigma xi yi divided by sigma xi square minus sigma xi y bar sigma xi square. As I told before, summation will only apply to the values which has an I subscript. If you see, this y bar is a constant which can be taken out. So I am going to take this out and write it like y bar sigma xi so that I can remove this. Okay. So sigma xi, this is simple x. So that means it is the same as writing sigma x minus x bar. And we have already proved that sigma x minus x bar is equal to 0. That means sigma simple xi is equal to 0, and which obviously means this whole part is equal to 0, and because of that this entire thing is equal to 0. That means this is not there. So basically this equation can be written like this. That is what I've written over here. The simple y becomes capital Y because this part of the equation gets cut. It's 0 basically. So ultimately I can write saying that beta 1 cap is equal to this sigma xi yi sigma x square. And over here what I'm going to do is I'm going to put this equal to, let me show you guys, this xi, and this one I'm going to give it a term. I'm going to say that is equal to k, simple ki. Okay, then we write out the rest of the stuff. So since we get this, we can say that beta 1 cap is a linear estimator because it's a linear function of yi. This is how we prove the fact that beta 1, the OLS estimator, is linear. Alright, how did we do? We took the beta 1 equation, and from this first equation, we proved that that is equal to this. And in the last final one which we got, what did we do? We took this part and set that equal to k. So because of that, we end up with sigma ki by I. So now we can say that this is a linear estimator because it's a linear function of capital Y. Alright. So here, if you all notice, we are using the CL1 assumption. That is obviously the parameters are linear in estimators. And even the CL3 assumption. What is CL3? CL3 is where we say there is a sampling variation in X. So if that is violated, that means if in case there is no sampling variation, that means the variance of X is 0, what will happen to beta 1? This denominator will be equal to 0, and because of that, beta 1 becomes undefined. But since CL3 is held true only, this is not equal to 0. This is not equal to 0, and therefore we are able to prove that it is linear. So here what we are going to say is that the fact that these OLS estimators are linear comes from the assumption CL1 and CL3. Okay. Next, let's move to unbiasedness. To prove unbiasedness, we have to take the same thing which we proved under linear. So we say beta 1 cap is equal to sigma ki by I. Alright, we start off with this. What is the end goal? We have to prove that expectation of beta 1 cap is equal to the beta 1 population value. Okay. To achieve this ultimate goal, let's go through the several steps. So sigma ki yi, that is okay. Now instead of yi, I can write down over here. This is the, instead of this, I can write down the population regression function. So population regression function goes as beta naught plus beta 1 xi plus ui. This is another sample regression function because it has the error term, right? This is a population regression. Okay. So I can write it like this. Then I will have to cross multiply each term. Ki into beta naught, that is sigma ki beta naught. Then when I multiply it with this, it will be sigma ki beta 1 xi. Then if I multiply this with this, it's sigma ki ui. Alright. Now whatever the constant terms, I'm going to take it out of the summation factor. So here if you see, we have beta naught which can be taken out, and here we have beta 1 which can be taken out. So once I take them out, it will be beta naught sigma ki. Likewise beta 1 sigma ki xi plus sigma ki ui. Betas have been taken out. Now I'm going to prove that sigma ki, that is this part, is equal to 0. Because of that, this entire thing becomes 0. And I'm also going to prove that this part is equal to 1. So because of that, beta 1 into 1 is beta 1. Right? Let's see how we get that. Let me write or completely finish this. Sigma ki ui. Okay. Let's see how we get this. So first, when we look into sigma ki, what is ki equal to? Here you can see now. Okay. So as you can see, this comes over here. Ki is equal to xi divided by sigma xi square. Now I'm gonna apply the summation function on both sides. So it will be sigma ki, and here also we'll apply sigma. Alright. So if I remove the brackets on this side, this will be sigma xi. Summation on summation is the same thing. So basically we have the denominator as sigma, the same thing actually, sigma xi square. Okay. We know for a fact that this is basically this one. Okay. So that is equal to 0. So I can say that this part is equal to 0. Yes. So because of that, sigma ki is equal to 0. We have proved this part now. Let's look into the next one. So that says sigma ki xi is equal to 1. Okay, let's see that. So sigma ki xi is equal to, instead of k, I can write xi sigma xi square. This is the value of k. Yes. And the rest of the stuff remains as it is. So sigma xi. What's the new part which I have added? This, that is equal to ki. Now the simple exercise can be written in the deviation form. How do we write it in the deviation form? Xi minus x bar. Even in the denominator, I can write sigma xi minus x bar whole thing square. Next, I'm going to cross multiply xi with xi, which is sigma xi square. Then if I multiply, this is not cross multiply, actually I'm removing the brackets. Then I multiply xi with x bar, it will be minus sigma xi x bar. Since x bar, this part is a constant that can be taken out, and I can put it over here x bar, so that I can remove this. The denominator, how do we solve the denominator? Like how we've learned in maths. We've learned this, right, guys? A plus b whole thing square is equal to a square plus b square plus 2ab. I'm going to apply that same concept over here. So because of that, the denominator would be this xi square minus, instead of b square we will have x bar square then instead of the 2ab we'll have 2 into xi into x bar. Okay, now remember the fact that we have a summation in front, so I will have to apply the summation all over here, here and here. If you all notice, this constant x bar can be brought out, so I can write that as x bar 2 sigma xi, so that I can remove this part. Like how we have learned before, x bar is equal to sigma xi divided by n. Therefore, we can say sigma xi is equal to n x bar. So wherever it says sigma xi, I am going to plug in n x bar. So here we have a sigma xi and here we have a sigma xi. So I'm going to write n x bar over there. So sigma xi square minus x bar n x bar divided by sigma xi square minus 2x bar nx bar and guys, if you see, here also we have an x bar, which is a constant which can be taken out. Yes, so if I take that, I'll write over here and show sigma x bar square. When I take that out, it will be x bar square. Within, after sigma there will be a 1. So like I said before, sigma runs from 1 to n. So if we add 1 n number of times, it is actually x bar square into n. So basically here I have, instead of this, I can write nx bar square. Okay, that comes from here. So if I simplify the whole thing, it will be sigma xi square minus nx bar square divided by sigma xi square. Here we have minus 2 nx bar, here we have plus 2 nx bar, so it's like minus 2 plus 1. So minus 2 and plus 1 is minus 1. So I can write it as minus nx bar square. I hope you have got this. This part can be written as 2nx bar square, right? Yes, I hope you all agree. This part can be written as 2nx bar square. So here we have minus 2nx bar square. Then next we have plus nx bar square, which can be written as minus nx bar square. So if you see the numerator and the denominator both are the same, so this is 1. So what did we want to prove? Sigma kixi, see, that is equal to 1. So we take that and plug it here. Okay. So when we plug that over there, beta 1 into 1, beta 1 remains as it is, and we get this. And this whole thing is equal to what? Beta 1. So beta 1 is simply beta 1 plus sigma kiui. Now what I'm going to do is I'm going to put the expectation function on both sides. And when I remove the brackets, it will be expectation of beta 1 plus expectation of sigma kiui. Okay, expectation of a constant is that constant itself. So here expectation of beta 1 would be beta 1. The second part of the equation, since expectation and summation, these two are linear operators. Okay, expectation, you can write this somewhere and keep expectation and summation, they are linear operators. Therefore we can switch their orders. Orders can be switched. Okay, so I can write this as sigma expectation of kiui. Okay, so since this a definite term which we have given a like xi over this part, for this part only we gave ki, right? So that can be brought out. So if you bring that out, we can write sigma ki expectation of ui plus beta 1. So beta 1 plus, you guys know now that the expectation of u according to what? According to the property which we have already learned. Expectation of the error terms is equal to 0. This basically comes under assumptions, guys. Okay. So if you are looking to CL3, CL3 says there is no sampling variation, and CL4 says that Xers are non-random in repeated sampling. Okay. So if you take this expectation of U given X, here we are saying that X's are fixed in repeated sampling. So thereby we can say this is coming from CL4A. And the X's which we are getting, we are saying that there is a sampling variation, that is CL3. So these two assumptions are satisfied over there. So because this part is 0, this entire part is 0, and we end up achieving our goal, basically, that is expectation of beta 1 is equal to beta 1. Yay! That's what we wanted to find, right? Here. Expectation. This is what we refer to as unbiasedness. So this is how we prove that beta 1 is an unbiased estimator. So since we are starting off with the answer which we got for linear, we are using CL1 and CL3 even in unbiased estimates. Okay, we have to use that in order to prove that it's unbiased. So CL1 and CL3 are definitely there. Other than that, we are using CL4 as well, saying that Xers are fixed in repeated sampling. In slide 30, there is a question asking, does the property of unbiasedness tell us how good the estimate we obtain from a sample is? Actually, no. The property of unbiasedness is actually like a theoretical concept, so it only tells us if the certain conditions, that is these CL1, CL3 and CL4A, if these conditions are satisfied or not. And it says whether the OLS estimates they are on average. See, we are saying that expectation of beta 1, if I zoom that out, we are by saying it's unbiased, what are we trying to prove? We are saying whether the mean is actually equal to the population parameter. So we are trying to say whether the OLS estimates will on average be equal to the population parameter. So basically it doesn't say anything specific to our sample. So even if we had got one sample, this is like an unbiased estimate, but is one sample enough to say whether the beta 1 is good or not? No. So it doesn't say anything about whether the estimate is good or not. Alright. And they're asking what are the practical situations in which this is useful. So this is very helpful in deriving the standard errors of our estimates. Okay. And what we mean by that is when we prove unbiasedness, later on you will understand, after we prove unbiasedness only we can prove whether they are best or not. That means whether they have the minimum variance or not. So only when the estimators have the minimum variance, I think I explained that before as well. Over here, see. So again, if I have to explain, when after we prove unbiasedness only, we can prove whether that unbiased estimator has minimum variance or not. So when it has minimum variance, then this denominator part will be low. So when the denominator is small, That means when the variance or the standard error is small, that means our t stat is going to be high, and it's very easy to prove that there is a significant relationship. So in order to prove individual significance of independent variables, this is very, very important, and this is how it becomes useful in practical situations. Next is where we have to speak about the part where it says best. Okay, here, this one. So as I explained before, we have several methods to find out the value for beta naught and beta 1. Okay, we have OLS, MLE, MM, and all. Okay, but if we use the OLS method, we are saying that they are not only linear and unbiased estimates, but within the group of linear and unbiased estimates which we have, OLS will give us the best estimates, that is the estimates with the minimum variance. So since they are most efficient, the standard errors are small. When the standard errors are small, in hypothesis testing, as you can see, the test statistic will be large, and we can prove individual significance. Likewise, if you take confidence intervals, when your standard error is small, your confidence interval is narrow. That means you can take decisions with high precision. In slide 31, we've been asked the question again whether the best estimate tell us whether how good the estimates we obtain from a sample are. Again, no, because like unbiased efficiency is also like a theoretical concepts which tell us whether if those certain conditions are satisfied, the OLS estimator is like a most efficient estimator to use. So it doesn't say anything specific to the sample. And they're asking this question, why do we have to really care about OLS being the best? So if they are not going to tell us how good the estimates are, why do we still have to worry and care about OLS being the best? That is because we for a fact very well know that when these conditions are satisfied, OLS will give us unbiased linear estimators, and these estimators are also considered as the best estimators. Okay, so this is best actually. Now we said no, when it comes to linear, CL1 and CL3 are the most important ones. When it comes to unbiasedness, even CL4A gets added. When it comes to best, we talk about CL5. So when CL5 is satisfied only, it becomes the best. So let's say in some, like a hypothetical thing, if we find that the CL5 is violated, that means is OLS still the best estimator? No, it's not going to provide us with the minimum variance. That means it's no point, no point of using OLS method right now, because it's not giving you the minimum variance. Then we have to go in search of another alternative other than OLS. That is why we have to give some consideration, and we have to care a bit about OLS being the best, because if it is the best, it's going to definitely give us with the minimum variance, so we can go ahead. If it's not the best, then it's not going to give you the minimum variance. That means we have to go in search of another alternative. So in best, since we are talking about the variance and standard errors, let's have a look into how the standard error, basically in this T stat C, we have divided by the standard error of beta 1. You guys actually know how to find the standard error? Still we haven't learned, right? So let's look into the equation of the standard error of beta 1. Like I said before, we don't give much preference to beta naught, but we'll look into the equation of beta naught as well. Okay, so let's write the topic. So the formula for standard error of beta 1 is equal to sigma square divided by x minus x bar square. This is the variance. We take the square root in order to find the standard error. So how you all can keep this, or how you all can remember these is this sigma square. It's the variance of error. How did the variance of error become equal to sigma square? Remember, in CL5, what do we say? CL5, we talk about homoscedasticity. If you are looking to that part of the video, we have mentioned that variance of the error term given x values is equal to the expectation of u square given x, which is actually sigma square. Why do we put a sigma square over there? Because we say the variance of the error terms is a constant value. Okay, homoscedasticity means variance is constant. So the variance of error over here, we put it as sigma square. That is how we got that sigma square. Then we divide the variance of error by the variance of x. Alright, so that is x minus x bar square. So this is how we get the standard error of beta 1. But the thing is, though we have included the variance of error in the numerator, this one, error is something which cannot be observed in reality. Okay, so this basically we cannot observe. So instead of the error, we have to use the residual as a proxy. Alright guys, so actually the error variance is sigma square. But since errors cannot be observed, we take the residual as a proxy and find the residual variance, which we denote as sigma square. We put a cap in top of it. This is basically the estimate for sigma square is this. So how do we calculate the residual variance where we have the sigma square cap? That is equal to the residual square, then we get the summation divided by n minus 2. This we have already learned in stat 2. In stat 2, what we refer to as standard error SSE is basically what we are talking about. So why is it n minus 2? Is it always n minus 2? No. If it's a bivariate regression, that means if you have included only one independent variable, then it's n minus 2. If not, this is n minus k plus 1. Remember guys, when we are finding the error, so this is basically the variance, the variance of errors, right? So actually, usually how do you find the variance? We divide it by the degrees of freedom. So how do we get the degree? Residuals is equal to y minus y cap. Okay, y cap is basically beta naught plus beta 1 x. So since we have 2 over here, we wrote it as n minus 2. Let's say we have 3. Let's say we have beta 1 x1 and beta 1 x2. There are 2 independent variables. 2 plus 1 is 3. So that is what comes here. 2 plus 1 is 3, n minus 3. Alright guys, so this is the formula for the residual variance. This is how we actually find the standard error. So if I plug this residual variance into the formula which we have got before, how would it look like? Standard error of beta 1 is equal to sigma square sigma x minus x bar square root. It's the same thing which I've written. What have I missed? We have to put the cap on this. Alright guys. This is called the standard error basically. This is the standard error. This is the estimated standard error. Okay. So this is the formula for beta 1. We learn the formulas for beta naught as well. So if I write it on this side, it will look like standard error of beta naught is equal to it's the same thing with a little bit of changes. So we write the same thing, sigma square divided by sigma x minus x bar square root. Difference is that we have to multiply the top part by xi square and the denominator by n. This is how we get the beta naught value. So since we cannot observe the sigma square which I mentioned, we have to find the estimated beta naught, which is equal to standard error of beta naught is sigma square x minus x bar square. We multiply with xi square on the top and n at the bottom. And put a cap. This is estimated beta naught variance. This is estimated beta 1 variance. Standard error basically, not the variance. If you put the square root, it's a standard error. So if you see in slide 36, they have asked the question, what do the standard errors of the estimators tell us about the estimators and why do we need to know them? So standard errors, what do they actually tell? They speak about the reliability and the precision of our estimates. If you all want to note it down, you all may write that down and keep. We specifically, when we are interpreting about variance and standard errors, what do we say? Reliability and precision. And actually, why do we need them? As I said before, in hypothesis testing, if we show that the standard error is small, then our t is large. When the standard error is small, our t is large, t stat is large. That means we can prove individual significance. Likewise, in confidence interval, I don't know whether you all remember confidence interval. How do we get the interval? It's basically the point estimate plus or minus the margin of error. What is the margin of error? It comprises of the table value into the standard error of beta 1. Okay, point estimate. Okay, so basically what I'm trying to say over here is, if your standard error is small, that means your confidence interval is small. So when your confidence interval is small, it shows you greater precision, and you can make decisions with greater precision. Alright guys, now in slide 37 they are asking this question: what does it mean by beta 1 and beta naught to have a variance? So I've explained this part before as well. Now we have only calculated beta 1, one value for beta 1 and one value for beta naught. So what do they actually mean by finding variance for one value? Actually, that means we are not finding only one value for beta 1 and beta naught. Since we are only taking one sample, we have got one value. But if we had got all possible samples of all all possible samples of same size, then we would have got different values for beta 1 from each sample, different values for beta naught from each sample, and then if we calculate the variance, we get an answer for that. And when we calculate the variance for the different values from beta naught from each sample, we get the actual variance. Okay, and if you look into slide 37, they've asked, how does the sample size affect the standard error? Okay, so if we look into that, how does the so if you take the numerator sigma square, this is not observable, so we use residuals as the proxy. That means we find sigma square cap, which is equal to the error term square summation divided by n minus 2. So if n is going to increase, if the sample size is going to increase, then the denominator is increasing. That means the variance is going to decrease. So our numerator is basically going to decrease. What happens to a denominator when we say sigma that applies to I running from 1 to n? Okay, so when our sample size increases, the number of square terms which we are gonna add is gonna increase. Basically, if I give an example now, let's say x minus x bar, the value is 5. Okay, so I'm saying sigma 5 from I1 to 2. Okay, so 5 square, I said x minus x bar is 5. That means 5 square is 25. So it's 25 plus 25 is 50. Now if I increase the sample size from I equals 1 to 4, then that means we are adding 25 4 times, which is equal to 100. So by increasing the sample size, see, this entire term has increased. So what is the effect of increasing the sample size? When we increase the sample size, the denominator is going to increase. So when the sample size is increased, numerator is decreasing, denominator is decreasing, they are increasing. Therefore, the ultimate effect on the standard error is a decreasing effect. So is it good or bad having a low standard error? It's actually good, as I've explained over here. When there are low standard errors, we can prove individual significance and high precision of the confidence interval. Alright guys. Then the last concept which we have to look into is the normality of error term. So because of the properties of OLS estimators, so far we didn't require the assumption about the distribution of U. Okay, we didn't have to care about the distribution of the error term. However, when we start to make inferences, we definitely need to know about the sampling distribution of the estimators. Okay, when we start to make decisions, obviously we have to know about the distribution of beta naught and beta 1, that is the estimators. So in order to do that, we have to make assumptions about the distribution of error term. So when we have this assumption of normality, when we make the assumption that the distribution of U is normal, that means we are saying that UI is following normal distribution. Actually, we say standard normal distribution with mean 0 and variance sigma square. So when we have this assumption, so far we mentioned that OLS estimators, they are blue. That means out of the linear unbiased estimates we have, this is the best one. Okay, but if we make this assumption saying that distribution of U is normal, then it's still no longer BLUE, but it's considered to be BUE. That means among the unbiased estimators we have, this is the best. So here we are only considering linear estimators. Out of the linear, we are saying OLS is the best. Okay. Here we are saying out of linear and non-linear, OLS will give you the best estimator as far as the distribution of the error term is normal. So what is actually better? This or this? This is much better, right? We are considering both the linear and non-linear estimators, not just linear. Okay, so when we make that assumption, we are considering both. And another thing is that by making this assumption about the distribution of the error term, we are sure about the sampling distribution of the regression estimators. So if we take beta 1 is said to follow normal distribution with mean beta 1 and standard error, as we have learnt already, sigma square sigma xi square. Okay, so we know the exact sampling distribution of the regression estimators based on the fact that the distribution of U is normal. Okay, so since we know that exactly, we can carry out the hypothesis test with more precision. But the thing is, even if we don't know the distribution of U, which is usually the case, okay, in reality we don't know the distribution of U and all, but in such cases also we can use this, because when n is large enough, according to central limit theorem, we can say that the distribution of U will be approximately normal. But this can be only applied when the sample size is large. When n is large, we can apply the central limit theorem, which says that sampling distribution of u is approximately normal. That means the problem arises only when n is small. This is only true for n is large. No? So when n is small, then this can be applied. So this is basically the end of statistical estimators, guys. So what you all have to know, you all now look into slide 41 if you all are having the slides. They have made a comparison between numerical and statistical properties. So they are saying numerical properties, as we have discussed, n1 to n5, they are always true irrespective of the fact CLRM assumptions are satisfied or not. But this doesn't work the same for statistical properties. Only if the assumptions are true, statistical properties, that is the desirable properties which is mentioned in the Gauss-Markov theorem, and other than that we have consistency and asymptotic normality as well. Yes, these are held true only when the assumptions are held true. Another thing is that numerical properties, this can be checked using data. That's why I specifically mentioned that numerical, when talking about numerical properties, we look into the sample regression line. Here, we look, but we can't prove anything or we can't check using data when it comes to statistical properties because they are purely theoretical. So only way to ensure that these statistical properties are held true is to check whether the assumptions are held true. So if the assumptions are working, if it's not violated, if they are all correct and held true, that means we can say that statistical properties are also held true. Okay. Next, when it comes to numerical properties, why did we actually worry about numerical properties? In order to get the formula for SST, SSR and SSC that is needed to find the R square formula, which is coefficient of determination, which actually tells how good the model you fitted is. That's the benefit of that's like the advantage of numerical properties. When it comes to statistical properties, what did we talk about? Statistical properties, everything is based on the fact whether the standard error of the estimates and the distribution, whether it's gonna give you and prove at the end. In hypothesis testings, we are trying to prove individual significance. Here, as I mentioned here. And in confidence interval, we are trying to find the interval with the highest precision. Alright. So at the end of this, they are saying numerical properties, you don't need to memorize, guys. You just have to know what are the properties, and basic idea of that is enough. But when it comes to statistical properties, you all need to know all these proofs, as you all can see on the screen. So this is what we have discussed so far under linear, unbiased and best. You all have to know how to denote this mathematically and also explain this in words. All right, guys, then thank you.